Welcome to this presentation today titled Scalable Hierarchical EMIR Analysis Techniques for Reticle-Scale Data Center SOCs. My name is Ali Laif. I'm a principal engineer at Qualcomm. I work at the implementation CAD team. I'm here on behalf to present on behalf of my colleagues. They are the co-authors of this paper. They were not able to attend today. Their names are Uday Kumar, Ida Kupam, Karthik PM, Tarun Kumar Reddy Kakarla, and Srinivas Arora. Let's get started. So the data center SOCs are rapidly becoming critical size, which means their large size represents really a challenge for the typical EMIR analysis techniques. This challenge is because of the huge runtime, compute, and memory requirements to run like SOC level EMIR analysis for such chips. Even if we wanted to run the analysis on the compute cluster subsystems, it easily can run for days. And if you want to run the flat, that can run for days. So you could say, why not just run for the subsystem clusters separately without running the full chip? But that's not possible because it's only when we run at the SOC level that we are able to observe and fix real variations at the interfaces. Without that, you risk running into failures of your chip and also like yield issues. Typically, people also use abstraction models like left and room to kind of like mitigate this issue of memory requirements and compute. But that also like brings in the inherent challenge of loss of accuracy. And because of these challenges of runtime, they become even more critical because basically you are not able to run the number of iterations needed to converge during the ECO phase. Because you cannot really run just one iteration and be done. Typically, you have to iterate because there are multiple things that are happening and the timing is the sign-off is being fixed. The other sign-off checks also are being converged. So you need to run multiple iterations, and that's not possible. Especially if you add another element to it, that the schedules designing such chips is actually becoming very strict because of the aggressive time to markets nowadays to deliver such chips. But these data center SOCs, while presenting these challenges, they also come with an opportunity. And the opportunity lies in the fact that this type of chips, they have a lot of repetitive architecture by nature. So if you look at the compute cluster, you will see that there is a lot of logic that is repetitive. And the foundation of this work that I'm going to present today actually kind of builds on this idea. But before I go into the details more, I want to, in the next slide, I want to touch a little bit again on why the analysis at SOC level is important. And second, why the current abstraction methods do not work in this case. So, a typical data center SOC will be composed of multiple compute subsystems. And they will be either abutted to each other or they will be separated by channels. And usually, before even we reach the analysis at the SOC level, this compute subsystem blocks would have already went through the full sign-off closure. So the primary focus actually when we go to the SOC level is we want to identify issues at the channel and at the subsystem boundaries, which is the area here, like in the orange sector. And if we fail to identify and fix those issues, as I said before, basically you run into challenges of your silicon is going to fail, or the yield is not going to be up to your expectation when you want to mass produce your chip. Some of the typical approaches to address this the challenge of being able to run a flat SOC EMIR analysis is to use abstraction models. Typically, you either use the left abstraction and you add to it the EPL models, which models the current distribution. But we know that the modeling of the currents in that case will not be accurate. So the current spatial model distribution will not be accurate at the bins of the left. So people try to address that by creating the ROM models, or reduced order models. Those are industry standard models that you can create by EDA tools. And these models, they come with better representation of the current distribution, but they come with a caveat or a problem, because if you use the ROM model to represent the subsystem, what happens is once the channel switches, you don't actually see the impact of the switching on the logic inside the subsystem. So then basically the question is, how can we come up with a solution that can kind of benefit from what we get from the abstraction, basically reducing the memory, the compute, and runtime, while addressing the challenges of accurate representation of the current distribution. And that's what we will be covering in this slide, which actually represents the core idea of this work. So, in the previous slide, I mentioned the importance and the goal of, and the primary focus of running the SOC, like EMIR analysis and the Scalable is we want to capture the failures at the channel. So the idea here is we need to keep those areas flat. Basically, the logic at the channel and the logic at the boundary of the subsystem. And that's what you see here in the blue color. And then from there, what we do is we keep one layer or two layers of the tiles inside the subblocks also flat. That's the green color. And then from there, we bridge by another tile or two using the raw models, because we said that the raw model representation is better in terms of representing the current distribution. And what you see in gray here is deep inside the core or inside the subsystems. It's modeled using REF and EPL curves. And as I explained, because of the repetitive nature of the subsystem, this data center SOCs, the gray area actually will represent the bigger part of your chip. So thanks to this approach, and basically because we are keeping flat the area in the channel, the logic in the channel, and the logic in the subsystem boundary, we are able to have accurate current distribution, and also the rate sharing will be accurate at all the layers, not only at the top layer. And also because we are flattening the channel and the subsystem, there will be correlated switching between the channel and the subsystem. What that means is when the channel switches, that switching propagates into the subsystem, and also when the subsystem boundary switches, it also propagates to the channel. So because of that, if you run vectorless analysis, you will be able to capture real issues and then fix them. And thanks to this modeling, we will not use the accuracy because of the accurate current modeling and the accurately correlated switching. So there is no loss of accuracy, but on the same side, at the same time, we're able to get the benefits of the abstraction, right? Having faster turnaround time and much less usage of memory and compute. And we're going to share some data on that in the upcoming slides. So the way we went about, or the team went about to deploy this methodology is basically first identify the repetitive tiles or blocks, and that should be easy for a block like data center SOC. And once that is done, then you need to generate REF and EPL models for those blocks and tiles. So that's done through simulation at the tile or block level, and then create the ROM reduced order models for those tiles and blocks as well, done again by using EDA tools. And then what we did is we picked like a smaller subsystem from the SOC, and we tried to correlate the flat RAM versus using this methodology to see that we actually good correlation. And because we are using like standard models like the LEF, EPL, and ROM, those are industry standard models, we believe that it will be straightforward to integrate this methodology in any existing flows that you might already have. So in this next slide, I wanted to share some real data from the application of this methodology to one of our real projects. And the things that easily you can see from this table is the runtime reduction. So by using this methodology, you were able to complete the full run of the SOC in 56 hours, almost 2 days and a half. How we went with the full flat SOC, it would have taken 10 days, which is unrealistic for us to do during the ECU phases. You can see also that the number of compute is reduced by 3x orders of magnitude, and the memory by 70%. Without actually giving up on the accuracy. So that allows us to run multiple iterations and therefore be able to predictably converge throughout our execution. And this brings me to the final slide. So basically what I described so far is the data center SOCs are becoming large. We believe that's very challenging to run the flat SOC analysis for EMIR. The methodology we propose is to keep flat the channel and the subsystem, and then add layer abstraction by using the ROM model on one or two layers of the tiles, and then keep the rest flat using the left-less EPL. With that, basically you get the accuracy of current distribution, and then you get the benefits of the abstraction in terms of reducing the runtime, the compute, and memory. And given the data that we shared and what we have observed, we believe that this solution allows to reduce by orders of magnitude the runtime, compute, and memory. And therefore, it's a way to go forward for such analysis of SOCs like data center SOCs. So that concludes my slides and my presentation. Thank you very much for your attention.